Welcome to Deep Sleep Studios, a place to calmly explore the most astonishing parts of our universe while helping you drift off to sleep. This is a place for gentle attention and unhurried curiosity, and also for letting go. Tonight, we'll drift through the great nebulae of our galaxy, those vast clouds of gas and dust where stars are slowly born. We'll witness the gentle pull of gravity gathering matter across millions of years, and we'll float through nurseries of light where infant suns take their first breath. If you're enjoying Deep Sleep Studios, you can like the video and subscribe for more gentle journeys like this. And if you'd like, leave a comment with where you're listening from and what time it is. It's comforting to know who else is out there quietly. Let your body settle now, wherever you are. Let your breathing find its own slow rhythm. We're about to leave the familiar world behind, rising up through the atmosphere, past the thin blue line that separates Earth from the endless dark. There's no hurry. There never is out here. The stars begin to appear, not twinkling now, but steady, constant points of ancient light. Each one a sun, some larger than our own, some smaller, all of them burning with the quiet fire of fusion. We're moving away from Earth now, watching it shrink behind us, a blue marble wrapped in swirls of white cloud. Our ship is gentle and unhurried. It moves through space the way a leaf drifts on still water, carried by currents we cannot see. The engines make no sound, of course. Sound needs air to travel, and out here there is only silence and starlight. We're heading toward a region of the sky that looks from Earth like a faint smudge against the blackness. But as we draw closer, that smudge begins to reveal its true nature. It is a nebula, a cloud of gas and dust so vast that it would take light years to cross from one side to the other. The word nebula comes from the Latin word for cloud or mist. Ancient astronomers saw these fuzzy patches in the night sky and wondered what they might be. Some thought they were distant galaxies. Others believed they were the birthplaces of stars. In time, we learned they were both and more. As we approach, the first wisps of the nebula begin to appear around us. They are impossibly thin, these gases far less dense than the best vacuum we could create on Earth. If you gathered all the matter in a cubic kilometre of this cloud, you might have enough to fill a thimble. Yet across the vast distances involved, that thin matter adds up to something magnificent. The colours begin to emerge now. At first, they are subtle, barely distinguishable from the black of space. A hint of rose here, a whisper of blue there. The nebula is illuminated by the stars within it and around it, their light exciting the atoms of gas and causing them to glow with their own soft radiance. We drift deeper into the cloud. The stars behind us begin to dim, veiled by the dust that hangs suspended in this cosmic fog. It's like entering a forest at twilight, watching the world outside fade as the trees close in around you. But there is nothing threatening here, only peace and the slow unfolding of creation. This particular nebula is what astronomers call an emission nebula. The gas within it is being energized by the ultraviolet light of young, hot stars, causing it to emit light of its own. The hydrogen glows red, the oxygen shimmers green and blue. The sulfur adds touches of gold and amber. Together, they paint a canvas that spans dozens of light years. We pass through a region where the gas is denser and the colors deepen around us. It's like swimming through a sunset that has been stretched across the heavens. The light is soft and diffuse, coming from no single direction, but surrounding us completely. We are inside the glow now, wrapped in it like a blanket of ancient light. Somewhere ahead, hidden within the thickest parts of this cloud, stars are being born. The process takes millions of years, far too slow for any human lifetime to witness. But we can see the evidence of it all around us, in the dark pillars of dust that rise like towers through the glowing gas, in the bright points of light that mark where new suns have already ignited. Let's drift toward one of those dark pillars now. It rises before us like a mountain made of shadow, its edges glowing where the light of nearby stars illuminates the dust. These structures are sometimes called elephant trunks or pillars of creation, and they are among the most beautiful sights in all the cosmos. The pillar is enormous, stretching for light years from base to tip. Within it, the dust and gas are slightly denser than in the surrounding nebula, shielding the interior from the harsh radiation of the young stars nearby. This creates a protected space, a cocoon where gravity can do its slow, patient work. We move closer to the pillar's surface. The dust here is made of tiny grains, some no larger than the particles of smoke from a candle flame. They are composed of carbon and silicon, of ice and iron, of all the elements that were forged in the hearts of ancient stars that died long ago. This dust is the raw material of worlds. If we could reach out and touch this dust, we would feel nothing. It is far too sparse, far too thin. But over millions of years, gravity draws these particles together, slowly, inexorably. A grain of dust drifts toward another grain. They touch, they stick, they become a slightly larger grain. And that larger grain attracts more dust and more and more. This is how it begins, the birth of a star. Not with fire and fury, but with the gentlest of touches, the softest of embraces. Dust gathering to dust across the vast, cold reaches of space. It is a process of infinite patience, and we are privileged to witness even this small part of it. We drift around the edge of the pillar now, and a new vista opens before us. Here, embedded in the column of dust, we can see several bright points of light. These are protostars, objects that are not yet true stars, but are well on their way to becoming them. They have gathered enough mass to begin heating up, to begin glowing with their own light. The nearest protostar is surrounded by a disk of material, a flattened ring of gas and dust that spirals slowly inward. This disk is the protostar's nursery, feeding it with fresh matter, helping it grow larger and hotter with each passing millennium. Someday, if all goes well, planets may form from the outer reaches of this disk. We approach the protostar carefully, keeping a respectful distance. Even though it has not yet ignited the nuclear fires that will make it a true star, it is already hot, already luminous. The temperature at its core has risen to hundreds of thousands of degrees, and it continues to climb as more matter falls inward. The disk around the protostar is beautiful in its own right. It catches the light of the young star and scatters it, creating a halo of gold and amber that extends for millions of kilometers. Within the disk, we can see darker bands where the dust is thicker and brighter regions where the gas has been heated to incandescence. Somewhere in that disk, the first seeds of planets may already be forming. Just as the star itself began with grains of dust sticking together, so too do planets begin their lives as tiny clumps of matter, slowly growing as they sweep up more material from the disk around them. It is a process that will take millions of years, but time means nothing out here. We drift away from the protostar now, letting its warm glow fade behind us. The pillar of dust rises on our left, and ahead we can see more of the nebula stretching away into the distance. The colors shift and change as we move, from deep reds to soft pinks to pale blues. Each region has its own character, its own story to tell. There is a quiet here that goes beyond mere silence. It is the quiet of deep time, of processes so slow that they make the rise and fall of human civilizations seem like the flicker of a candle flame. The nebula has been here for millions of years, and it will remain for millions more. We are just passing through, brief visitors to an ancient place. We come upon a region where the gas is particularly dense, forming a dark cloud against the brighter background of the nebula. This is what astronomers call a Bok globule, named after the astronomer Bart Bok, who first studied them in detail. These small dark clouds are often the sites of active star formation. The globule is roughly spherical, perhaps a light year across. Its edges are sharp against the glowing gas behind it, like a drop of ink suspended in water. Within that dark sphere, hidden from our view, gravity is at work. Matter is falling inward, gathering at the center, heating up as it compresses. We cannot see inside the globule with visible light. But if we had instruments that could detect infrared radiation, we would see a warm glow at its heart. That glow is the signature of a protostar in the making, still wrapped in its cocoon of dust, still gathering the mass it needs to ignite. It will be another 100,000 years, perhaps, before this protostar grows hot enough to begin fusing hydrogen in its core. When that moment comes, a new star will be born, and its light will begin to eat away at the globule that surrounds it. Eventually, the cocoon will disperse, and the young star will emerge into the wider nebula, joining its siblings in the great stellar nursery. We drift past the globule and continue deeper into the nebula. The light around us shifts to a deeper red, the color of hydrogen gas excited by stellar radiation. This is the most common element in the universe, the simplest atom, just one proton and one electron. Yet from this simple building block, all the complexity of the cosmos emerges. Ahead, we can see a cluster of young stars that have already emerged from their birth clouds. They shine with a fierce blue-white light, far brighter and hotter than our own sun. These are massive stars, perhaps 10 or 20 times the mass of the Sun, and they burn through their fuel at a prodigious rate. Such stars live fast and die young, at least by cosmic standards. While a star like our Sun might burn for 10 billion years, these blue giants will exhaust their hydrogen in just a few million years. Then they will swell into red supergiants and finally explode in spectacular supernovae, scattering their enriched matter back into the nebula. But for now, they are young and bright, and their light is shaping the nebula around them. The intense radiation from these stars pushes against the surrounding gas, carving out bubbles and cavities in the cloud. The edges of these bubbles glow brightly where the gas is compressed and heated by the stellar wind. We pass near one of these young stars, feeling the warmth of its light even across the vast distance that separates us. It is a reminder that stars are not just points of light in the sky, but furnaces of unimaginable power, converting matter into energy at rates that dwarf anything we could create on Earth. The star's light illuminates a nearby column of dust, and we can see the shadow it casts stretching away into the nebula. It's a strange thing to see shadows in space, but here they are, dark fingers reaching across the glowing gas. The interplay of light and shadow gives the nebula a three-dimensional quality, a sense of depth and structure. We drift into one of these shadows now, and the light around us dims. The glow of the nebula is still visible on either side, but directly ahead, the dust column blocks our view. It's like passing behind a cloud on a sunny day, watching the world grow momentarily darker before the light returns. Within this shadow, the temperature drops slightly. The dust here is cold, just a few degrees above absolute zero. It has been cold for millions of years, shielded from the warming light of the nearby stars. In this frigid darkness, molecules form that could not exist in warmer regions. Complex chains of carbon and hydrogen, the building blocks of organic chemistry. Scientists have detected more than 200 different molecules in the cold clouds of nebulae. Some of them are simple, like water and carbon dioxide. Others are surprisingly complex, like amino acids, the components of proteins. The chemistry of life may have its origins in places like this, in the cold, dark hearts of stellar nurseries. We emerge from the shadow, and the light returns, soft and diffuse. Ahead, we can see another structure in the nebula, a ring of glowing gas surrounding a central star. This is what remains of a star that shed its outer layers late in its life, creating a shell of expanding gas that now glows in the light of the hot core left behind. This is not a birthplace, but a grave, a reminder that the cycle of stellar life includes death as well as birth. But even in death, stars give back to the cosmos. The gas expelled by dying stars enriches the nebula with heavy elements, the products of nuclear fusion in the star's core. These elements will be incorporated into the next generation of stars and planets. We pass the ring nebula at a respectful distance, watching its delicate structure shimmer in the starlight. The central star, now a white dwarf, is small and dense, no larger than the Earth, but containing the mass of the Sun. It will cool slowly over billions of years, eventually fading to a cold, dark cinder. but the gas it expelled will live on, mixing with the rest of the nebula, becoming part of new stars, new planets, perhaps new life. In this way, the death of one star contributes to the birth of others. The cosmos recycles its matter endlessly, building new wonders from the ashes of the old. We continue our journey through the nebula, drifting now toward a region where the gas is thinner and the stars are more visible. Here we can see dozens of young stars scattered across our field of view, each one a recent graduate of the stellar nursery. They are moving apart slowly, carried by their own momentum, but for now they still form a loose cluster. These open clusters, as astronomers call them, are common in the galaxy. They form when a single cloud of gas gives birth to many stars at once, and they stay together for millions of years before the gravitational influences of passing stars and gas clouds gradually pull them apart. Eventually, each star will go its own way, wandering alone through the galaxy. But for now, they are together, siblings of a sort, born from the same cloud, sharing the same composition. If we could analyze the light of each star, we would find that they contain the same mix of elements, the same chemical fingerprint that marks them as members of the same family. We drift among these young stars, watching their light play across the remnants of the nebula that birthed them. Some of them may have planets already, small worlds forming in the disks of dust that still surround them. Others may be alone, solitary suns burning in the darkness. Each one has its own future, its own story yet to unfold. The light here is gentler than near the massive blue stars we passed earlier. These are smaller suns, more like our own, burning with a steady yellow or orange glow. They will live for billions of years, providing warmth and light to whatever planets may orbit them. Perhaps around one of them, life is already beginning to stir. We leave the cluster behind and drift toward the edge of the nebula. The gas grows thinner here, and the stars of the background galaxy begin to appear, no longer veiled by dust. We are approaching the boundary between the stellar nursery and the wider cosmos, the place where the nebula meets the void. Looking back, we can see the nebula spread out behind us, a vast canvas of colour and light. The pillars of dust rise like monuments. The young stars shine like jewels. The dark globules hang like drops of ink against the glow. It is a sight of indescribable beauty, a reminder of the creative power of gravity and time. Gravity is the gentlest of forces, the weakest of the four fundamental interactions. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. Yet gravity is also the most patient force, working ceaselessly across the vast distances of space, never tiring, never stopping. Given enough time, it can move mountains, build worlds, ignite stars. The nebula we have been exploring is a testament to gravity's patient power. Every structure we have seen, from the smallest grain of dust to the largest star, exists because gravity drew matter together across the empty reaches of space. Without gravity, the universe would be a formless void, a thin soup of particles with no structure, no beauty, no life. We drift now into a quieter region of space, leaving the nebula behind. The stars here are older, more widely spaced. They have had time to drift apart from their birth clusters to find their own paths through the galaxy. Some of them may be billions of years old, veterans of countless orbits around the galactic center. Our journey takes us toward another nebula now, one that lies in a different part of the galaxy. This one is darker, colder, a place where star formation has not yet begun in earnest. It is a molecular cloud, a vast reservoir of hydrogen and helium laced with traces of heavier elements. Here, the raw material of stars waits in the darkness, patient and still. The molecular cloud is invisible in ordinary light, revealing itself only as a dark patch against the starry background. But if we could see in infrared or radio waves, we would perceive its true extent, a complex structure of filaments and cores, of dense regions and empty voids. It is a landscape of shadow, a place of potential waiting to be realized. We enter the cloud slowly, watching the stars fade around us. The darkness here is profound, deeper than any night on Earth. The dust is so thick that almost no light penetrates from outside. We are in a cocoon of shadow, surrounded by matter that has been gathering here for millions of years. The temperature in this cloud is just a few degrees above absolute zero. At these temperatures, the molecules of gas move slowly, almost lazily. They drift through the void, occasionally colliding with one another, sometimes sticking together to form larger clumps. It is a slow dance, a minuet of matter playing out across the ages. Deep within the cloud, we come upon a dense core, a region where the gas and dust have gathered more thickly than in the surrounding material. This core is perhaps a light year across, containing enough matter to form a star and a system of planets. But for now, it is just potential, a seed waiting for the right conditions to sprout. The core is slowly contracting under its own gravity. The process is so gradual that it would be imperceptible on human timescales. But over thousands of years, the core grows denser, more compact. As it contracts, it heats up, the gravitational energy being converted into thermal energy. The center of the core is already warmer than its edges. In another 100,000 years, give or take, this core will become a protostar. The contraction will accelerate, the temperature will rise, and eventually the core will begin to glow with its own light. A new star will be on its way to being born, here in this dark and silent place. We drift away from the core, leaving it to its slow transformation. The molecular cloud stretches around us in all directions, a vast cathedral of shadow. Here and there, we can see other dense cores, other sites of potential star formation. Each one is a story waiting to be told, a future waiting to unfold. The silence here is absolute. There is no light to see by, no sound to hear. Only the patient drift of matter through the void, the slow gathering of dust and gas under gravity's gentle pull. It is a peaceful place, a place of waiting and becoming. Nothing is rushed here. Everything happens in its own time. We emerge from the molecular cloud and find ourselves in a region of space where the stars are more numerous. This is the plane of the galaxy, the disk of stars and gas and dust that makes up the Milky Way. Looking in one direction, we can see the glow of the galactic center, a dense concentration of ancient stars surrounding a supermassive black hole. Looking in the other direction, we see the outer reaches of the galaxy, where the stars grow fewer and the darkness of intergalactic space begins. We are somewhere in between, in the spiral arms where star formation is most active, where nebulae bloom like flowers in a cosmic garden. Our journey takes us now toward one of the most famous nebulae in the sky, a place that has been studied and photographed countless times, yet never loses its power to inspire wonder. It is the Orion Nebula, visible from Earth as a faint smudge in the sword of the constellation Orion. As we approach, the nebula reveals itself in all its glory. It is a vast cavern of glowing gas, carved out of a larger molecular cloud by the radiation of the young stars at its heart. The colors are breathtaking, ranging from deep reds to soft pinks to pale blues and greens. It is like a sunset frozen in space, a painting made of light and gas. The Orion Nebula is one of the closest stellar nurseries to Earth, just about 1,350 light-years away. It is also one of the most active, with hundreds of young stars in various stages of formation. Some are still wrapped in their cocoons of dust, others have already emerged to shine brightly in the nebular glow. At the heart of the nebula lies a group of 4 massive stars known as the trapezium. These stars are the primary source of the ultraviolet radiation that illuminates the nebula, causing the hydrogen gas to glow with its characteristic red light. They are young stars, perhaps only a few 100,000 years old, but they are already shaping the environment around them. We drift toward the trapezium, watching the 4 stars grow brighter as we approach. They are arranged in a rough trapezoid shape, hence their name. The brightest of them is about 40 times the mass of our Sun and nearly 200,000 times as luminous. It is a furnace of incredible power, burning through its hydrogen fuel at a furious rate. The radiation from the trapezium stars is slowly eroding the molecular cloud that surrounds the nebula. The ultraviolet light heats the surface of the cloud, causing the gas to evaporate and flow away. This process is creating the cavern we see, hollowing out the cloud from the inside. At the edges of the cavern, we can see dramatic structures where the evaporating gas meets the cooler material of the molecular cloud. These are the proplyds, short for protoplanetary disks, young stars surrounded by disks of dust and gas that are being sculpted by the radiation from the trapezium. We approach one of these proplyds, a young star surrounded by a teardrop-shaped envelope of glowing gas. The disk of dust around the star is visible as a dark silhouette against the bright background of the nebula. It is being slowly eroded by the radiation from the nearby massive stars, its outer layers stripped away like leaves in a wind. Despite this erosion, the proplyd may still have enough material to form planets. The inner regions of the disk are shielded from the worst of the radiation, and the process of planet formation may already be underway. In a few million years, this young star may have a family of worlds orbiting around it. We drift away from the proplid and continue our exploration of the Orion Nebula. Everywhere we look, there are wonders to behold. Here, a pillar of dust rises from the floor of the cavern, its surface glowing where the radiation strikes it. There, a dark globule hangs suspended in the glowing gas, a future star waiting to be born. The nebula is alive with activity, yet it all happens so slowly that it appears frozen in time. The pillars of dust will take thousands of years to erode. The globules will take hundreds of thousands of years to collapse into stars. We see only a snapshot, a single frame from a movie that has been playing for millions of years. We come upon a region where the gas is particularly bright, a knot of luminosity that stands out against the surrounding glow. This is a Herbig-Haro object, a patch of gas that has been heated and excited by a jet of material from a young star. These jets are common in stellar nurseries, narrow streams of gas ejected from the poles of protostars as they accrete matter from their surrounding disks. The jet that created this Herbig-Haro object is moving at hundreds of kilometers per second, far faster than any rocket we have ever built. When it collides with the surrounding gas, it creates a shock wave that heats the material to incandescence. The result is a bright knot of emission, a signpost marking the presence of a young star hidden within the dust. We follow the jet back toward its source, tracing the narrow stream of gas through the nebula. It leads us to a dense clump of dust, within which we can barely make out the glow of a protostar. The young star is still gathering mass, still growing, and the jet is a byproduct of that process, a release valve for the angular momentum of the infalling material. The protostar will continue to eject jets for thousands of years until it has gathered enough mass to begin fusing hydrogen in its core. Then, the jets will fade, the disk will disperse, and the star will emerge as a fully formed sun, ready to shine for billions of years. We leave the Herbig-Haro object behind and drift toward the edge of the Orion Nebula. The glow of the gas begins to fade, and the dark molecular cloud that surrounds the nebula becomes visible. This cloud is the parent of the nebula, the reservoir of matter from which the young stars have formed. The molecular cloud is vast, stretching for hundreds of light years across this region of the galaxy. The Orion Nebula is just one small part of it, a bubble of light carved out of the darkness. Elsewhere in the cloud, other nebulae are forming, other stars are being born. The entire region is a factory of stellar creation. We pass through the boundary between the nebula and the molecular cloud, entering the darkness once more. The stars of the trapezium fade behind us, their light absorbed by the dust. We are in the cold heart of the cloud now, surrounded by matter that has been waiting here since before the dinosaurs walked the earth. The silence is profound, the darkness is complete. Yet there is nothing threatening about this place. It is simply quiet, simply still. A place of potential, a place of becoming. The stars that will form here will shine long after humanity is gone, their light carrying the legacy of this moment into the far future. We drift through the molecular cloud for a long time, watching the subtle variations in density that mark the structure of the material. Here, the gas is slightly thicker, forming a filament that stretches across our path. There, it is thinner, creating a void through which we can glimpse the distant stars. The filaments are important structures in molecular clouds. They are the highways along which matter flows, the channels that feed the dense cores where stars form. Gravity draws the gas toward the filaments, and then along them toward the cores. It is a slow, patient process, but it is inexorable. We follow one of these filaments, tracing its path through the cloud. It leads us toward a particularly dense region, a place where several filaments converge. Here, the matter is gathering more quickly, the cores are more numerous. This is a hub of star formation, a place where many suns will be born. We can see the cores scattered through this region, dark knots against the slightly less dark background of the cloud. Each one is a potential star, a seed waiting to sprout. Some of them will produce single stars, others will produce binaries, or even multiple star systems. A few may produce massive stars that will burn brightly and die young. We approach one of the cores, drifting slowly into its outer regions. The dust here is cold and still, undisturbed by any wind or current. It has been gathering for millions of years, grain by grain, molecule by molecule. Now it is dense enough that its own gravity is beginning to pull it inward. The core is perhaps 1/10 of a light year across, containing roughly the mass of our Sun. At its center, the density is highest, the temperature slightly warmer. This is where the protostar will form, where the matter will gather and heat until it begins to glow with its own light. But that moment is still far in the future. For now, the core is dark and quiet, a cocoon of shadow in the heart of the molecular cloud. We rest here for a moment, suspended in the stillness, contemplating the vast timescales of cosmic creation. The universe is patient. It has been building stars for nearly 14 billion years, and it will continue to do so for trillions of years to come. Each star is a miracle of physics, a balance between the inward pull of gravity and the outward push of radiation pressure. Yet they form by the billions, scattered across the galaxies like grains of sand on a beach. We leave the core behind and continue our journey through the molecular cloud. The darkness begins to lighten as we approach the far side, the dust growing thinner, the stars becoming visible once more. We are emerging from the cloud, returning to the light. The view that greets us is spectacular. We have emerged near a cluster of young stars, a group of perhaps 100 suns that form together from the same cloud. They are still close together, bound by their mutual gravity, shining with the combined light of a small galaxy. The cluster is surrounded by the remnants of the nebula that birthed it, wisps of glowing gas that have not yet dispersed into the wider cosmos. The light of the young stars illuminates these wisps, creating a halo of color around the cluster. It is like a crown of light, a celebration of stellar birth. We drift among the stars of the cluster, watching their light play across our ship. Some of them are blue and hot, massive stars that will live fast and die young. Others are yellow or orange, more modest suns that will burn for billions of years. A few are red, small and cool, stars that will outlive the galaxy itself. The diversity of the cluster is remarkable. All these stars formed from the same cloud, at roughly the same time, yet they are so different from one another. The mass of a star is determined by the amount of matter that gathers in its core during formation, and this depends on subtle variations in the initial conditions of the cloud. We pass near a binary star system, two suns orbiting around their common center of mass. They are close together, separated by only a few million kilometers, and they complete an orbit every few days. Their gravitational dance has been going on since they formed, and it will continue for as long as they both shine. Binary stars are common in the universe. Perhaps half of all stars have at least one companion, bound together by gravity. Some binaries are so close that they share material, their outer atmospheres merging into a common envelope. Others are so far apart that they take thousands of years to complete a single orbit. We leave the binary behind and drift toward the edge of the cluster. The stars grow fewer here, and the darkness of space begins to close in. We are approaching the boundary between the cluster and the wider galaxy, the place where the gravitational influence of the cluster fades and the stars begin to go their separate ways. Over millions of years, this cluster will gradually disperse. The gravitational tugs of passing stars and gas clouds will pull its members apart, sending them on their own individual journeys through the galaxy. Eventually, the cluster will cease to exist as a distinct entity, its stars scattered across thousands of light years. But for now, they are together, a family of suns sharing the same corner of the cosmos. We take a moment to appreciate this sight, this gathering of stellar siblings, before continuing on our journey. Our path takes us now toward a different kind of nebula, one that is not a birthplace but a memorial. It is a supernova remnant, the expanding shell of gas left behind when a massive star exploded at the end of its life. These remnants are among the most beautiful and dramatic objects in the cosmos. As we approach, we can see the shell of gas expanding outward from the site of the explosion. It is moving at thousands of kilometers per second, far faster than any spacecraft we have ever built. Yet, across the vast distances of space, it appears frozen, a bubble of light suspended in the darkness. The colors of the supernova remnant are different from those of the star-forming nebulae we visited earlier. Here, we see the glow of oxygen and neon, of sulfur and silicon, elements that were forged in the core of the dying star and scattered into space by the explosion. These are the ashes of a sun, the remains of a stellar furnace. The explosion that created this remnant happened thousands of years ago, perhaps tens of thousands. The light from the supernova would have been visible from Earth, a new star appearing suddenly in the sky, bright enough to be seen in daylight. Then it would have faded over the following months, leaving behind this expanding shell of gas. We drift into the remnant, passing through the outer layers of the shell. The gas here is hot, heated by the shock wave of the explosion to temperatures of millions of degrees. It emits X-rays and ultraviolet light, radiation that would be deadly to unprotected humans. But we are safe in our ship, watching from a distance. At the center of the remnant, we might find a neutron star or a black hole, the collapsed core of the star that exploded. These objects are incredibly dense, packing the mass of a sun into a sphere just a few kilometers across. They are the ultimate remnants of stellar death, the final stage in the life cycle of a massive star. We do not approach the center too closely. The gravitational field near a neutron star or black hole is intense, capable of warping space and time in ways that would be dangerous to navigate. Instead, we observe from a safe distance, watching the shell of gas expand outward into the cosmos. The supernova remnant will continue to expand for thousands of years, eventually merging with the general interstellar medium. The heavy elements it carries will mix with the gas and dust of the galaxy, becoming part of the raw material for future generations of stars and planets. In this way, the death of one star contributes to the birth of others. We leave the supernova remnant behind and continue our journey. The stars around us are older now, more widely spaced. We have drifted into a quieter region of the galaxy, far from the active, star-forming regions we explored earlier. Here, the pace of cosmic change is slower, the drama less intense. We come upon a planetary nebula, a shell of gas surrounding a dying star. Unlike the supernova remnant, this nebula was created by a star that died more gently, shedding its outer layers over thousands of years rather than exploding all at once. The result is a delicate structure of glowing gas, often with intricate patterns and symmetries. This particular planetary nebula is roughly spherical, a bubble of gas expanding outward from the central star. The star itself is visible at the center, a hot white dwarf that illuminates the surrounding gas with its ultraviolet radiation. The gas glows with the colors of hydrogen and oxygen, red and blue and green. Planetary nebulae have nothing to do with planets, despite their name. The term was coined by early astronomers who thought these round, fuzzy objects resembled the disks of planets seen through their telescopes. The name stuck, even after we learned their true nature. The central star of this nebula was once a sun, much like our own, perhaps slightly more massive. It spent billions of years on the main sequence, fusing hydrogen into helium in its core. Then, as the hydrogen ran out, it swelled into a red giant, its outer layers expanding to engulf any planets that might have orbited close by. Finally, the outer layers were expelled into space, creating the nebula we see today. The core of the star, now exposed, contracted and heated up, becoming the white dwarf at the center. It will cool slowly over billions of years, eventually fading to a cold, dark cinder. We drift through the planetary nebula, watching the light of the central star play across the expanding shell of gas. The structure is more complex than it first appeared, with rings and jets and knots of brighter emission. These features are created by the interaction of the stellar wind with the surrounding material, sculpting the nebula into its final form. The nebula will last for only a few tens of thousands of years, a brief moment in cosmic terms. Then the gas will disperse into the interstellar medium, and only the white dwarf will remain, a silent monument to the star that once shone here. We leave the planetary nebula behind and continue our journey through the galaxy. The stars around us are a mix of ages and types, from young blue giants to ancient red dwarfs. Each one has its own history, its own story of birth and life and eventual death. We pass near a red dwarf star, a small, cool sun that will burn for trillions of years. These are the most common stars in the galaxy, outnumbering all other types combined. They are dim and unassuming, easy to overlook. Yet they will be the last stars shining when all the others have burned out. The red dwarf has a small planet orbiting close to it, a rocky world not much larger than Earth. The planet is tidally locked, always showing the same face to its star, with one hemisphere in perpetual day and the other in perpetual night. The boundary between the two, the terminator, might be the most habitable region where temperatures are moderate. We do not know if life exists on this world. The conditions are harsh by Earth standards, with the star's frequent flares bathing the planet in radiation. Yet life is tenacious, and it might find a way to survive even here. We will never know for certain, but we can imagine. We drift away from the red dwarf and its planet, continuing our journey through the stars. The galaxy stretches around us in all directions, a vast spiral of light and shadow. We are just one small ship in an ocean of stars, a mote of consciousness in a universe of unimaginable scale. Our path takes us now toward another nebula, one that lies in a different spiral arm of the galaxy. This one is a reflection nebula, a cloud of dust that shines not with its own light, but with the reflected light of nearby stars. The colors are different here, blues and whites predominating, the scattered light of hot young suns. The reflection nebula is beautiful in a different way than the emission nebulae we visited earlier. The light is softer, more diffuse, like moonlight on a misty night. The dust particles that make up the nebula are tiny, just fractions of a micrometer across, and they scatter blue light more efficiently than red. This is why the nebula appears blue, just as the sky on Earth appears blue. We drift through the reflection nebula, watching the light shift and change around us. The dust is not uniform, but clumpy, creating regions of brighter and dimmer illumination. Here and there, we can see dark lanes where the dust is thicker, blocking the light from behind. The stars that illuminate this nebula are young, perhaps only a few million years old. They formed from the same cloud of gas and dust that now reflects their light. In time, their radiation will disperse the nebula, scattering the dust into the wider cosmos. But for now, they are wrapped in a cocoon of their own making, a shroud of reflected glory. We leave the reflection nebula behind and continue our journey. The stars grow fewer as we drift toward the outer reaches of the spiral arm, approaching the gap between the arms where the density of stars is lower. Here, the darkness is deeper, the silence more profound. we come upon a globular cluster, a dense ball of ancient stars that orbits the galaxy in a halo above and below the disk. These clusters are among the oldest objects in the cosmos, containing stars that formed more than 12 billion years ago, when the universe was young. The globular cluster is a spectacular sight, a swarm of hundreds of thousands of stars packed into a sphere just a few hundred light-years across. At the center, the stars are so close together that they would appear as a continuous glow, a river of light flowing across the sky. We drift toward the cluster, watching it grow larger in our view. The stars at the edges are more widely spaced, but as we approach the center, they become more numerous, more densely packed. The light is golden here, the color of old stars, suns that have been burning for longer than the Earth has existed. The stars in a globular cluster are all roughly the same age, born together from the same cloud of primordial gas. They have been orbiting the galaxy ever since, a self-contained community of ancient suns. No new stars form in globular clusters. The gas was used up long ago, leaving only the stars themselves. We pass through the outer regions of the cluster, watching the stars drift by on either side. They are moving, of course, orbiting the center of the cluster under the influence of their mutual gravity. But the timescales are so long that they appear motionless to our eyes, frozen in their ancient dance. At the heart of the cluster, we might find exotic objects, blue stragglers, stars that appear younger than they should be, perhaps the result of stellar mergers, millisecond pulsars, neutron stars spinning hundreds of times per second, perhaps even black holes, the remnants of the most massive stars that once shone here. We do not venture too deep into the cluster. The density of stars at the center is too great, the risk of collision too high. Instead, we observe from a safe distance, appreciating the beauty of this ancient gathering of suns. We leave the globular cluster behind and continue our journey, drifting now back toward the disk of the galaxy. The stars grow more numerous again, the familiar patterns of the spiral arms becoming visible. We are returning to the realm of active star formation, the places where nebulae bloom and new suns are born. Our journey takes us toward one more nebula, a place of particular beauty and significance. It is the Carina Nebula, one of the largest and brightest nebulae in the sky, a vast complex of gas and dust where some of the most massive stars in the galaxy are being born. As we approach, the nebula fills our view, a panorama of color and light that stretches across dozens of light years. The structure is complex, with pillars and towers of dust, bubbles and cavities carved by stellar winds, bright knots of emission and dark lanes of absorption. It is a landscape of cosmic proportions, a testament to the creative power of gravity and radiation. At the heart of the nebula lies Eta Carinae, one of the most massive and luminous stars known. It is a binary system, two giant stars orbiting each other in a complex dance. The more massive of the two is perhaps 100 times the mass of our Sun and 5 million times as luminous. It is a star on the edge of destruction. Eta Carinae has already experienced one major outburst in the 1840s, when it briefly became the second brightest star in the sky. The explosion ejected a vast cloud of gas and dust, creating the distinctive hourglass shape that surrounds the star today. This cloud is still expanding, still glowing with the light of the central star. We approach Eta Carinae carefully, keeping a respectful distance. The star is unstable, prone to further outbursts, and it may explode as a supernova at any time. When it does, it will be one of the most spectacular events in the history of the galaxy, visible from Earth even in daylight. But for now, it burns on, a beacon of light in the heart of the Carina Nebula. Its radiation is shaping the surrounding gas, carving out cavities and pillars, triggering the formation of new stars in the compressed edges of the cloud. It is a destroyer and a creator, a star that gives even as it takes. We drift away from Eta Carinae and explore the wider nebula. Everywhere we look, there are wonders to behold. Here, a pillar of dust rises like a tower, its surface glowing where the radiation strikes it. There, a cluster of young stars shines brightly, their combined light illuminating the surrounding gas. We pass through a region where the gas is particularly dense, a dark cloud that blocks the light from behind. Within this cloud, stars are forming, hidden from our view. We can see the jets that some of them are ejecting, narrow streams of gas that punch through the cloud and glow where they collide with the surrounding material. The Carina Nebula is a place of intense activity, a factory of stellar creation on a grand scale. Hundreds of stars are forming here, perhaps thousands. Some of them will be massive giants like Eta Carinae, destined to live fast and die young. Others will be modest suns like our own, burning steadily for billions of years. A few will be tiny red dwarfs, barely visible even from close range. We drift through the nebula for a long time, exploring its many wonders. The colors shift and change as we move, from deep reds to soft pinks to pale blues. The structures vary from delicate wisps to massive pillars, from tiny knots to vast bubbles. It is a landscape of infinite variety, a place that could be explored for lifetimes and never fully known. Eventually, we reach the far side of the nebula and emerge into the clearer space beyond. The glow of the Carina Nebula fades behind us, a memory of light and color. We have traveled far, seen much, and it is time to begin the journey home. We turn our ship and set a course back toward Earth, back toward the familiar stars of our own neighborhood. The journey will take us through regions of space we have already explored, past nebulae and clusters and solitary suns. But we are in no hurry. There is always time for one more look, one more moment of wonder. As we travel, we reflect on what we have seen, the nebulae, those vast clouds of gas and dust where stars are born, the protostars gathering mass in their cocoons of shadow, the young stars emerging into the light, shaping the gas around them with their radiation, the old stars shedding their outer layers, returning their matter to the cosmos. It is a cycle as old as the universe itself, a dance of creation and destruction that has been playing out for nearly 14 billion years. Stars are born, they live, they die, and from their ashes, new stars are born. The matter of the cosmos is recycled endlessly, building new wonders from the remains of the old. And through it all, gravity is the constant, the gentle force that holds everything together. It draws the dust into clouds, the clouds into cores, the cores into stars. It holds the stars in their orbits, the planets in their paths, the galaxies in their clusters. Without gravity, the universe would be chaos. With it, the universe is a symphony. We pass through a region of space where the stars are particularly numerous, a dense field of suns that stretches across our view. Each one is a point of light, a distant furnace burning with the fire of fusion. Some of them may have planets. Some of those planets may have life. We will never know for certain, but we can wonder. The stars begin to thin as we approach the edge of this region, and the familiar constellations of Earth's sky begin to appear. Orion rises before us, his belt of 3 bright stars pointing the way home. The Pleiades glimmer to one side, a cluster of young stars that have been a landmark for human navigators for thousands of years. We are almost home now, almost back to the small blue world where our journey began. The Earth grows larger in our view, its oceans and continents becoming visible, its atmosphere a thin blue line against the blackness of space. It is a fragile world, a tiny oasis of life in the vast desert of the cosmos. We descend through the atmosphere, feeling the gentle tug of gravity as we return to the surface. The stars fade from view, replaced by the blue sky of day or the dark sky of night. We are back on Earth, back in the familiar world of air and water and solid ground. But we carry with us the memory of what we have seen, the nebulae glowing with the light of newborn stars, the molecular clouds, dark and cold and full of potential, the supernova remnants, the ashes of dead suns scattered across the cosmos, the globular clusters, ancient gatherings of stars that have been shining since the universe was young. These wonders are always there, whether we see them or not. They continue their slow dance of creation and destruction, their patient gathering and dispersing, their endless cycle of birth and death and rebirth. The universe is alive with activity, even when it appears still. The cosmos is always becoming, always changing, always new. And gravity, gentle gravity, is the force that makes it all possible. The weakest of forces, yet the most patient. The force that builds worlds and ignites stars, that holds galaxies together and shapes the structure of the cosmos. Without gravity, there would be no nebulae, no stars, no planets, no life. With gravity, the universe is a place of infinite wonder. Let these thoughts carry you now as you drift toward sleep. The universe is vast, but it is not empty. It is full of light and color, of structure and beauty. And you are part of it, made of the same matter that forms the stars, the same elements that were forged in the hearts of ancient suns. You are stardust, gathered by gravity into the form of a human being. You are the universe become conscious, able to wonder at its own existence. And tonight, as you sleep, the stars will continue to shine. The nebulae will continue to glow, and the gentle force of gravity will continue its patient work of creation. Rest now. Let your breathing slow. let your thoughts quiet. The universe will still be there when you wake, vast and beautiful and full of wonders. But for now, there is only this moment, this breath, this gentle drifting towards sleep. The nebulae are waiting, patient and still. The stars are burning, bright and warm. And gravity, gentle gravity, is holding everything together, keeping the cosmos in its endless dance. You are safe, you are held, you are part of something vast and beautiful and eternal. Sleep now. Dream of nebulae and stars, of dust and light, of the gentle pull of gravity gathering matter across the endless reaches of space. Dream of creation and wonder, of silence and peace. The universe is with you, always, in every atom of your being. And when you wake, the stars will still be shining, the nebulae will still be glowing, and the dance of creation will continue, as it has for billions of years, as it will for billions more. You are part of that dance, a brief but beautiful note in the symphony of the cosmos. Rest now. The universe is holding you. Gravity is holding you. Sleep is holding you. Let go and drift and dream. The journey continues, even in sleep. The stars are always there, waiting to be explored. The nebulae are always there, glowing with the light of creation. And you are always there, a spark of consciousness in the vast dark, a witness to the wonders of the cosmos. Sleep well, dream deeply, and know that you are never alone. The universe is with you, always, in every breath, in every heartbeat, in every dream. You are part of something vast and beautiful and eternal, and nothing can ever take that away. The nebulae are waiting. The stars are shining. Gravity is gentle, and sleep is coming, soft and warm and deep. Let it carry you now, into the quiet dark, into the peaceful stillness, into the dreamless rest that waits at the end of every journey. You have travelled far tonight. You have seen wonders beyond imagination. And now it is time to rest, to let go, to drift into the gentle embrace of sleep. The universe will be there when you wake, vast and beautiful, and full of new wonders to explore. But for now, there is only this moment, this breath, this gentle drifting towards sleep. The stars are fading, the nebulae are dimming, and the soft darkness of rest is closing in around you. Let it come, let it carry you, let it hold you in its gentle arms. Sleep now. The universe is at peace, and so are you. The last light of the nebulae fades from your mind, replaced by the soft darkness of sleep. The stars are still there, shining in the distance, but they are quiet now, peaceful, content to wait until you return. The journey is over for now. The rest has begun, and in the silence, in the stillness, in the gentle dark, the universe continues its eternal dance. Stars are born, stars die, matter gathers and disperses, and gravity, gentle gravity, holds it all together. The cycle continues, as it always has, as it always will. You are part of that cycle. You are made of stardust, gathered by gravity, shaped by time. And tonight, as you sleep, you are returning to the stillness from which all things come, the peace that underlies all creation. Rest now. Dream of nebulae and stars. Dream of dust and light. Dream of the gentle pull of gravity, gathering matter across the endless reaches of space. And know that when you wake, the universe will still be there, vast and beautiful and full of wonders, waiting for you to explore. Sleep well. The cosmos is holding you. The stars are watching over you. And gravity, gentle gravity, is keeping you safe, holding you close, cradling you in its infinite embrace. The journey is over. The rest has begun. And in the silence, in the stillness, in the gentle dark, you are at peace. Sleep now. Dream deeply. And know that you are loved by the universe, held by the stars, cradled by gravity. You are part of something vast and beautiful and eternal, and nothing can ever take that away. The nebulae are waiting, the stars are shining, and you are drifting gently, peacefully, into the deep and dreamless sleep that waits at the end of every journey. Rest now. The universe is at peace, and so are you. In the quiet of this moment, as sleep draws near, consider the vastness of what we have witnessed together. The nebulae stretch across light years, their colours painted by the light of young stars. The molecular clouds hang in the darkness, cold and patient, waiting for gravity to begin its slow work of creation. These are places of profound stillness, where time moves differently than it does on Earth. A human lifetime is less than a heartbeat to a nebula. The rise and fall of civilizations is barely a flicker. Yet in that brief flicker, we have learned to see these wonders, to understand them, to appreciate their beauty. The stars that form in nebulae will shine for millions or billions of years. Some of them will have planets, and some of those planets may harbour life. Perhaps around some distant sun, another consciousness is looking up at the night sky, wondering about the universe, dreaming of distant worlds. We are not alone in our wonder. The universe is vast, and it may be full of minds like ours, gazing at the stars, asking the same questions, feeling the same awe. We are part of a great community of consciousness, scattered across the galaxies, united by our shared capacity for wonder. And at the heart of it all is gravity, the gentlest of forces, the most patient of sculptors. Gravity does not rush. It does not force. It simply draws things together, slowly, inevitably, across the vast reaches of space and time. It is the force that makes stars possible, that makes planets possible, that makes life possible. Without gravity, the universe would be a formless void, a thin soup of particles with no structure, no beauty, no meaning. With gravity, the universe is a place of infinite wonder, a tapestry of light and shadow, a symphony of creation and destruction. You are held by gravity right now, as you lie in your bed, as you drift towards sleep. The same force that draws dust together in nebulae, that ignites stars in their cores, that holds galaxies in their spirals, is holding you to the earth, keeping you safe, cradling you in its gentle embrace. Let that thought comfort you as you drift towards sleep. You are part of the universe, made of the same matter, shaped by the same forces. You are stardust, gathered by gravity, animated by the energy of ancient suns. You are a miracle of physics, a wonder of creation, a brief but beautiful note in the symphony of the cosmos. And tonight, as you sleep, the universe continues its eternal dance. Stars are born in distant nebulae. Planets form in disks of dust. Life stirs on worlds we have never seen. The cycle continues, as it always has, as it always will. You are part of that cycle. You are part of that dance, and nothing can ever take that away. Sleep now. Let the thoughts of nebulae and stars fade into the background, becoming a gentle hum, a soft lullaby. Let the images of dust and light dissolve into the darkness, becoming part of the peaceful stillness that surrounds you. The universe is at rest, and so are you. The stars are shining, but they are quiet now, content to wait until you return. The nebulae are glowing, but their light is soft, gentle, soothing. Everything is at peace. Let your breathing slow. Let your body relax. Let your mind drift, like a leaf on still water, like a mote of dust in a sunbeam, like a star in the gentle embrace of a nebula. You are safe. You are held. You are loved by the universe, cradled by gravity, watched over by the stars. There is nothing to fear, nothing to worry about, nothing to do but rest. The journey is over. The exploration is complete. And now it is time to sleep, to dream, to rest in the peaceful stillness that waits at the end of every journey. Sleep now. The universe is holding you. The stars are watching over you. And gravity, gentle gravity, is keeping you safe, holding you close, cradling you in its infinite embrace. Rest well, dream deeply, and know that when you wake, the universe will still be there, vast and beautiful and full of wonders, waiting for you to explore. But for now, there is only this moment, this breath, this gentle drifting towards sleep. The nebulae are waiting, the stars are shining, and you are at peace. Sleep now. The darkness is soft and warm, like a blanket wrapped around you. The silence is deep and peaceful, like the stillness at the heart of a nebula. There is nothing to disturb you, nothing to wake you, nothing but the gentle drift toward dreamless sleep. Let go now. Let go of the day. Let go of your thoughts. Let go of everything but this moment, this breath, this peaceful stillness. The universe is with you, the stars are with you, gravity is with you, and sleep is with you, soft and warm and deep. Rest now. The journey is over. The exploration is complete, and the peaceful stillness of sleep is waiting for you, just a breath away, just a heartbeat away, just a moment away. Let it come. Let it carry you. Let it hold you in its gentle arms. Sleep now. Dream of nebulae and stars. Dream of dust and light. Dream of the gentle pull of gravity, gathering matter across the endless reaches of space, and know that you are loved. Know that you are held. Know that you are part of something vast and beautiful and eternal. Sleep well. The universe is at peace, and so are you. The last thoughts fade now, like stars at dawn, like nebulae dispersing into the void. There is only stillness, only peace, only the gentle embrace of sleep. Rest now. Dream deeply. And know that the universe is holding you, always, in every moment, in every breath, in every dream. Sleep now. The journey is over, and the peaceful rest of sleep is here. Let it carry you into the quiet dark. Let it hold you in its gentle arms. Let it cradle you in its infinite embrace. Sleep now. The universe is at peace, and so are you. And in the silence, in the stillness, in the gentle dark, you drift away, carried by the soft currents of sleep, cradled by the gentle force of gravity, held by the loving arms of the universe. Sleep well, dream deeply, and rest in peace. The nebulae are waiting, the stars are shining, and you are at rest. Sleep now. The cosmos holds you gently, as it holds all things. The same gravity that gathers dust into stars, that shapes galaxies into spirals, that bends light around massive objects, is holding you now, keeping you grounded, keeping you safe. There is comfort in that thought. You are not separate from the universe. You are part of it, woven into its fabric, connected to every star and nebula and planet. The atoms in your body were forged in the hearts of ancient suns. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it came from stars that died billions of years ago. You are stardust, dreaming of stars. You are the universe, contemplating itself. And tonight, as you sleep, you return to the stillness from which all things come, the peace that underlies all creation. The nebulae continue their slow dance of creation, far away in the depths of space. Stars are being born even now in clouds of gas and dust that we will never see. Planets are forming, moons are coalescing, and somewhere, perhaps, life is taking its first tentative steps. The universe is alive with activity, even in its quietest moments. But you do not need to witness it all. You do not need to understand it all. You only need to rest, to sleep, to dream. The wonders of the cosmos will still be there when you wake. The nebulae will still be glowing, the stars will still be shining, and the gentle force of gravity will still be doing its patient work of creation. Nothing is lost by sleeping. Everything is gained by resting. So let go now. Let go of the need to see, to know, to understand. Let go of the day and its concerns. Let go of everything but this moment, this breath, this peaceful drifting towards sleep. The universe is holding you. The stars are watching over you. And gravity, gentle gravity, is keeping you safe. Sleep now. Rest deeply and know that you are loved. The darkness closes in, soft and warm. The silence deepens, peaceful and still, and you drift away, carried by the gentle currents of sleep, cradled by the loving arms of the universe. Sleep well. Dream of nebulae and stars. Dream of dust and light. Dream of the gentle pull of gravity, gathering matter across the endless reaches of space. And know that when you wake, the universe will still be there, vast and beautiful and full of wonders, waiting for you to explore. But for now, there is only sleep, only rest, only peace. The journey is over, the exploration is complete, and the gentle embrace of sleep is here, waiting to carry you into the quiet dark. Let it come. Let it hold you. Let it cradle you in its infinite embrace. Sleep now. The universe is at peace, and so are you. Rest well, dream deeply, and know that you are part of something vast and beautiful and eternal. The nebulae are waiting, the stars are shining, and you are at rest. Sleep now, And in the silence, in the stillness, in the gentle dark, you are at peace. The universe holds you. Gravity holds you. Sleep holds you. Rest now, dream now, sleep now. The journey is over. The rest has begun. And you are at peace. Sleep. Deep sleep. Studios, nebulae, star nurseries, gentle gravity. Part 2. Continuing the gentle journey. To continuation, the stellar nurseries' deeper chambers. As we drift further into the stellar nursery, we discover that these cosmic cradles hold even more wonders than we first imagined. The glowing pillars of gas we explored earlier are merely the entrance to a vast and intricate realm where the universe conducts its most patient work. Let us continue our gentle journey, floating deeper into the luminous mists where new mysteries await our peaceful contemplation. Chapter 13. The Protostellar Disk. Around a young star still gathering its strength, we discover a remarkable structure, a vast disk of gas and dust that swirls in an elegant spiral, like cream slowly stirring into cosmic coffee. This is a protostellar disk, and it tells a story of creation that extends far beyond the birth of a single star. The disk stretches across distances that dwarf our entire solar system. If we could somehow see it from above, it would appear as a great pinwheel of light and shadow, rotating with the patience of deep time. The material closest to the young star moves quickly, completing its orbit in mere days. But the outer reaches of the disk turn so slowly that a single rotation might take thousands of years. Within this spinning disk, something remarkable is happening. The dust particles, tiny grains of silicates, carbon, and ice, are beginning to find one another. Like snowflakes drifting together in a gentle wind, these microscopic specks are colliding and sticking, growing grain by grain into larger and larger clumps. This is how planets are born. The process is almost impossibly gradual. A dust grain might drift for centuries before encountering another particle of just the right size and velocity to stick rather than bounce away. But the universe has nothing but time, and slowly, inevitably, the grains become pebbles. The pebbles become boulders. The boulders become mountains of rock and ice, tumbling through the disk in their endless orbital dance. We watch as one such growing object, a planetesimal, astronomers call it, sweeps through the disk. It is perhaps a kilometre across now, a tiny worldlet still far too small to pull itself into a spherical shape. Its surface is rough and irregular, covered in the accumulated debris of countless gentle collisions. As it moves through the disk, it acts like a cosmic vacuum cleaner, its gravity, weak but growing, attracting nearby particles. Each collision adds to its mass, and each addition of mass increases its gravitational reach. It is a feedback loop of patient accumulation, a slow-motion avalanche of growth. The light from the young star filters through the disk, creating bands of brightness and shadow. In some regions, the dust is so thick that it blocks the starlight entirely, creating dark lanes that wind through the glowing material like rivers of shadow. In other areas, the disk has begun to clear, swept clean by the growing planetesimals that have claimed all the available material. These gaps in the disk are signposts of planetary formation. Each dark ring marks the orbit of a world in the making, a future planet that is slowly emerging from the cosmic raw materials. Some of these forming worlds will become gas giants, growing so large that they can capture vast atmospheres of hydrogen and helium. Others will remain smaller and denser, rocky worlds that might one day harbour oceans, atmospheres, and perhaps even life. The temperature varies dramatically across the disk. Close to the young star, the heat is intense enough to vaporize most materials. Only the most refractory substances, metals and certain minerals, can survive in solid form. This is why the inner planets of most solar systems tend to be rocky and dense. But further out, beyond a boundary that astronomers call the frost line, the temperature drops low enough for water to freeze. Here, ice becomes a building material as common as rock. The planets that form in these outer regions can grow much larger, their cores of rock and ice massive enough to capture thick atmospheres from the surrounding disk. We drift toward this frost line, watching as the character of the disk changes. The dust here sparkles with countless ice crystals, each one a tiny prism that catches the distant starlight and scatters it into subtle rainbows. The material is fluffier, lighter, more abundant. This is where the giant planets of the future will take shape. A young gas giant is already forming here, a world perhaps 10 times the mass of Earth. It has grown large enough to begin capturing gas from the surrounding disk, wrapping itself in a thick atmosphere that will eventually dwarf the solid core at its center. Storms already swirl in its upper atmosphere, though these are not storms of water and air, but of hydrogen and helium, exotic clouds of ammonia and methane. The forming giant has cleared a wide gap in the disk around its orbit. Its gravity reaches out like invisible hands, shepherding the nearby material, preventing it from drifting inward toward the star. In this way, giant planets help to shape the architecture of entire solar systems, determining where smaller worlds can form and where they cannot. We watch as a stream of gas spirals down from the disk onto the growing giant. The material doesn't fall straight down, but instead curves inward along the planet's magnetic field lines, creating glowing auroras at the poles that dwarf anything seen on Earth. The planet is still hot from its formation, radiating more energy into space than it receives from the distant star. The disk itself will not last forever. Already, the radiation from the young star is beginning to erode its outer edges, blowing the lightest gases away into interstellar space. In a few million years, the disk will be gone entirely, dispersed by stellar winds and consumed by the planets it has created. What remains will be a solar system, a star surrounded by its family of worlds, each one a frozen record of the conditions that existed when it formed. But for now, the disk remains, and we float within it, surrounded by the raw materials of worlds yet to be. The dust and gas that swirl around us might one day become mountains and oceans, atmospheres and ice caps. Every grain of matter here carries the potential for something greater, waiting only for time and gravity to reveal its destiny. The silence of this place is profound. There is no sound in space, no rushing of wind or rumble of thunder, though the forces at work here are powerful beyond imagination. The disk rotates in perfect quiet, its spiral arms unwinding in slow motion, its forming planets growing grain by grain in the endless patience of cosmic time. We let ourselves drift with the rotation, becoming part of the great wheel of creation that turns around the young star. The dust particles that pass by us are older than any artifact on Earth, forged in the hearts of stars that died billions of years ago. And yet they are also the raw materials of the future, the building blocks of worlds that will not exist for millions of years to come. This is the paradox of the protostellar disk. It is simultaneously ancient and newborn, a recycling of old materials into new forms. The iron in these dust grains was forged in a supernova explosion. The carbon was breathed out by a dying red giant star. The water ice crystallized from gases that have drifted through the galaxy for eons. All of it has come together here in this swirling disk to begin the process of creation anew. The light grows softer as we drift toward the outer edges of the disk. Here, far from the warmth of the young star, the temperature drops to just a few tens of degrees above absolute zero. The ices here are not just water, but also frozen carbon dioxide, methane, nitrogen, and more exotic compounds. These outer reaches are a cosmic deep freeze, preserving materials in their pristine state for billions of years. Comets are born in these frozen outer regions. We watch as a small, icy body takes shape, a loose aggregation of frozen gases and dust that will one day be flung into the inner solar system by the gravitational influence of the giant planets. When that happens, the heat of the star will vaporize its surface, creating the glowing tail that gives comets their name. But for now, it drifts in frozen silence, waiting for its moment in the distant future. The disk extends even further, fading gradually into the darkness of interstellar space. There is no sharp boundary, no clear edge where the disk ends and the void begins. Instead, the material simply grows thinner and thinner, the spaces between particles growing larger, until finally there is nothing but the empty darkness between the stars. We hover at this threshold, looking back at the glowing disk and the young star at its center. From here, the entire system appears as a bright point of light surrounded by a faint halo of dust. It is beautiful in its simplicity, a single star with its retinue of forming worlds, one small island of creation in the vast ocean of space. And yet, this scene is being repeated across the galaxy, in thousands of stellar nurseries just like this one. Each young star has its own disk, its own forming planets, its own potential for worlds and moons, and perhaps even life. The universe is a factory of solar systems, producing new worlds with the same patient efficiency that it produces new stars. We turn away from the disk and drift deeper into the nebula, seeking new wonders in the glowing mists ahead. Chapter 14. The Bok Globules. Scattered throughout the stellar nursery like dark seeds waiting to sprout, we find small, dense clouds that astronomers call Bok globules. Named after the astronomer who first studied them, these compact clouds are among the coldest and darkest objects in the universe, and they are also among the most fertile. Each Bok globule is a potential stellar system in waiting. The clouds are small by cosmic standards, typically only a light year or so across, but they are incredibly dense. The material within them is packed so tightly that almost no light can penetrate to their cores. From the outside, they appear as dark silhouettes against the glowing background of the nebula, like ink blots on a canvas of light. We approach one of these dark clouds, watching as it grows larger in our view. The edges of the globule are not sharp, but ragged, with wisps of dark material trailing away like smoke from a dying fire. These wisps are being eroded by the radiation from nearby stars, slowly eating away at the cloud's outer layers. But the core remains protected, shielded from the harsh stellar radiation by the thick blanket of dust and gas that surrounds it. The temperature inside a Bok globule can drop to just 10 degrees above absolute zero, colder than almost anywhere else in the universe. At these temperatures, even the random motions of atoms slow to a crawl. The gas becomes so cold that it can no longer support itself against its own gravity, and it begins to collapse. We drift into the outer layers of the globule, and the light fades around us. The glowing nebula disappears behind a curtain of darkness, and we find ourselves in a realm of profound shadow. The only illumination comes from the faint infrared glow of the dust itself, a warmth so subtle that it would be invisible to human eyes. But our journey takes us deeper still, into the very heart of the globule, where something remarkable is happening. Here, in the absolute darkness, a new star is being born. The collapse has been going on for thousands of years, and it has created a dense core of material at the center of the cloud. This core is not yet a star. It doesn't have enough mass or temperature to ignite nuclear fusion, but it is well on its way. Astronomers call it a protostar, a stellar embryo still gathering the material it needs to begin its life as a true star. The protostar glows with infrared light, the heat of gravitational compression radiating outward through the surrounding dust. This warmth is the first sign of the star's awakening, a gentle announcement that something new is emerging from the darkness. The temperature at the protostar's surface is perhaps 1,000 degrees, hot enough to glow a dull red, but still far cooler than a mature star. Material continues to rain down onto the protostar from the surrounding cloud. The infalling gas and dust form a disk around the young object, similar to the protostellar disk we explored earlier, but smaller and more compact. Jets of material shoot outward from the protostar's poles, punching through the surrounding cloud and creating cavities that allow some light to escape. These jets are one of the most dramatic features of stellar birth. They can extend for light years, ploughing through the interstellar medium and creating glowing shock waves where they collide with surrounding material. The jets carry away angular momentum from the forming star, allowing the collapse to continue. Without them, The protostar would spin faster and faster until it tore itself apart. We watch as one of these jets erupts from the protostar, a beam of superheated gas moving at hundreds of kilometers per second. The jet glows with the light of excited atoms, creating a brilliant streak of blue-white light that cuts through the darkness of the globule. Where the jet strikes the wall of the surrounding cavity, it creates a bow shock, a curved wave of glowing gas that looks like the wake of a cosmic speedboat. The jet is not continuous, but episodic, erupting in bursts as material falls onto the protostar in clumps. Each burst creates a new knot of glowing gas that moves outward along the jet, like beads on a string. By studying these knots, astronomers can read the history of the protostar's feeding, tracing the irregular rhythm of its growth over thousands of years. The opposite jet extends in the other direction, creating a symmetrical pattern of outflow. Together, the two jets form what astronomers call a bipolar outflow, a cosmic fountain that sprays material back into the interstellar medium. Some of this material will eventually fall back onto the forming star, while the rest will escape into the broader nebula, contributing to the raw materials for future generations of stars. We drift along one of the jets, following its path through the Bok globule and out into the surrounding nebula. The transition is dramatic, from absolute darkness to brilliant light, from cold silence to warm illumination. The jet has carved a tunnel through the globule, and we emerge into a cavity filled with reflected starlight. Looking back, we can see the globule as a dark mass silhouetted against the glowing nebula. The jets emerge from opposite sides, creating bright streaks that extend far beyond the boundaries of the cloud. This is what stellar birth looks like from the outside. A dark cocoon pierced by beams of light, a hidden process revealed only by its most energetic outbursts. But the Bok globule is not alone. Scattered across this region of the nebula, we can see dozens of similar dark clouds, each one at a different stage of collapse. Some are still round and quiescent, their cores not yet dense enough to begin forming stars. Others show the telltale signs of active star formation, jets, outflows, and infrared glows that betray the presence of protostars within. In a few million years, all of these globules will have produced their stars. The dark clouds will disperse, blown away by the radiation and winds from their newborn stellar children. What remains will be a cluster of young stars, a stellar family born from the same parent cloud. These siblings will drift together through the galaxy for millions of years before gradually separating, each star going its own way into the cosmic void. We pause to contemplate this cycle of creation and dispersal. The Bok globules are temporary structures, lasting only a few million years before they either form stars or are eroded away by external radiation. And yet, they are constantly being replenished as new dense regions form within the larger nebula. The process of star formation is continuous, a never-ending cycle of collapse and birth that has been going on for billions of years. The darkness of the globules is not emptiness, but potential. Within each dark cloud lies the possibility of a new star, a new solar system, perhaps even new worlds, where life might one day arise. The universe hides its most creative work in shadow, revealing it only when the process is complete and a new star emerges to light up its surroundings. We drift away from the Bok globules, carrying with us a sense of the patient, hidden work that goes on in the darkest corners of the nebula. The journey continues, and new wonders await. Chapter 15. The Herbig-Haro Objects. As we travel through the stellar nursery, we encounter some of the most beautiful and dynamic objects in the cosmos. The Herbig-Haro objects, named after the astronomers who first catalogued them. These are the visible manifestations of the jets we saw emerging from the Bok globules, the places where high-speed outflows from young stars collide with the surrounding interstellar medium. Each Herbig-Haro object is a work of cosmic art, a sculpture of light and gas shaped by the forces of stellar birth. They come in an astonishing variety of forms: bow shocks and jets, knots and filaments, loops and spirals. No two are exactly alike, yet all share the same fundamental nature. They are the visible evidence of the violent processes that accompany the peaceful growth of new stars. We approach a particularly beautiful example, a bow shock that curves gracefully through the nebula like the prow of an invisible ship. The shock front glows with the characteristic colors of excited atoms, the blue-green of oxygen, the red of hydrogen, the subtle purple of nitrogen. These colors tell us about the composition and temperature of the gas, a cosmic palette that reveals the physics of the collision. The bow shock is moving through the nebula at tremendous speed, perhaps 200 kilometers per second. At this velocity, the gas cannot simply flow around the obstacle, but instead piles up in a compressed wave. The compression heats the gas to tens of thousands of degrees, causing it to glow with the light we see. Behind the bow shock, the gas cools and expands, creating a turbulent wake that trails off into the surrounding medium. The source of this bow shock is a young star hidden deep within a nearby Bok globule. We cannot see the star itself. It is still shrouded in its birth cloud, but we can see the effects of its jets as they plow through the nebula. The jet that created this bow shock was launched thousands of years ago, and it has been traveling through space ever since, carrying with it the energy and momentum of the forming star. We follow the jet back toward its source, passing through a series of knots and condensations that mark previous eruptions. Each knot is a separate Herbig-Haro object, a frozen record of a moment in the star's early life. By measuring the distances between the knots and their velocities, astronomers can reconstruct the history of the jet, reading the star's growth like rings in a tree trunk. The knots are not stationary, but moving, each one traveling outward from the source at its own velocity. Sometimes faster knots catch up with slower ones, creating collisions that produce new shock waves and new regions of glowing gas. The jet is a dynamic, evolving structure, constantly changing as new material is ejected and old material disperses. We pause at one of these knots, a compact region of glowing gas, perhaps the size of our solar system. The light here is intense, the gas heated to temperatures that would vaporize any solid material. And yet, within this inferno, we can see structure, filaments and wisps that trace the magnetic field lines, dense cores that have somehow survived the passage of the shockwave. The magnetic field plays a crucial role in shaping the Herbig-Haro objects. The gas in the jet is ionized, stripped of its electrons by the intense heat. And this ionized gas interacts strongly with magnetic fields. The field lines act like invisible rails, guiding the flow of material and preventing it from spreading too quickly. This is why the jets remain so narrow and collimated, even after traveling for light years through the interstellar medium. We drift through the knot, surrounded by the glow of excited atoms. The light here is not the steady shine of a star, but a flickering, pulsing illumination that changes as the gas cools and recombines. Electrons are captured by ions, releasing photons of specific colors as they cascade down through the energy levels. This is the light of atomic physics made visible, the quantum mechanics of individual atoms painted across the canvas of space. Beyond this knot, the jet continues its journey through the nebula. We follow it further, watching as it gradually fades and disperses. The energy of the original eruption is being shared with the surrounding medium, heating the interstellar gas and contributing to the overall turbulence of the nebula. Eventually, the jet will lose its identity entirely, its material mixing with the general flow of the stellar nursery. But before that happens, the jet encounters an obstacle, a dense clump of gas that lies directly in its path. The collision creates a spectacular display, a complex of shock waves and glowing filaments that spreads across the sky like a cosmic flower. This is one of the largest Herbig-Haro objects in the region, a testament to the power of stellar jets and the richness of the interstellar medium. The clump is being sculpted by the impact, its outer layers stripped away by the force of the collision. In time, the jet may punch entirely through the clump, creating a tunnel of hot gas that connects the two sides, or the clump may prove too dense, deflecting the jet and sending it careening off in a new direction. The outcome depends on the details of the collision, the density of the clump, the velocity of the jet, the strength of the magnetic field. We watch this cosmic collision unfold in slow motion, the changes too gradual to perceive directly, but evident in the structure of the shock waves. The Herbig-Haro object is a snapshot of a process that has been going on for centuries and will continue for centuries more. We are witnessing a moment in a story that began long before we arrived and will continue long after we depart. The beauty of the Herbig-Haro objects lies not just in their appearance, but in what they represent. They are the visible signs of stellar birth, the announcements that new stars are emerging from the darkness. Each jet, each bow shock, each glowing knot is a message from a young star, a declaration of existence sent out into the cosmos. And the universe is full of such messages. Herbig-Haro objects are found throughout the stellar nurseries of the Milky Way, wherever young stars are forming and jets are being launched. They are among the most common signposts of star formation, visible evidence of a process that is usually hidden from view. We take one last look at the Herbig-Haro complex before continuing our journey. The glowing filaments stretch across our field of view, a tapestry of light woven by the forces of stellar birth. It is a reminder that the universe is not static but dynamic, constantly creating and destroying, building and dispersing. The peace we feel in these cosmic spaces is not the peace of stillness, but the peace of balance, the equilibrium of forces that are always in motion. The journey continues, and new wonders await. Chapter 16. The Evaporating Gaseous Globules. At the edges of the stellar nursery, where the radiation from young stars meets the cold darkness of the surrounding cloud, we find some of the most poignant structures in the cosmos, the evaporating gaseous globules, or EGGs. These small, dense knots of gas are the last survivors of a larger cloud that has been eroded away by stellar radiation, and they represent a race against time in the process of star formation. Each EGG is a potential star in the making, a dense core of gas and dust that may or may not have enough mass to collapse and ignite. The radiation from nearby young stars is slowly eating away at the globules' outer layers, like ice cream melting in the sun. If the collapse can proceed fast enough, a new star will be born. If not, the globule will evaporate entirely, its material dispersed into the surrounding nebula. We approach one of these globules, a dark teardrop shape silhouetted against the bright background of ionized gas. The globule is perhaps a few hundred astronomical units across, small by cosmic standards, but still large enough to contain the mass of several Jupiters. Its surface is being sculpted by the stellar radiation, creating a smooth, streamlined shape that points away from the nearest bright star. The boundary between the globule and the surrounding ionized gas is sharp and well-defined. On one side, the gas is cold and neutral, shielded from the radiation by the dense material of the globule. On the other side, the gas is hot and ionized, glowing with the light of excited atoms. This boundary is called an ionization front, and it marks the advancing edge of the stellar radiation. The ionization front is moving into the globule, converting neutral gas into ionized plasma at a rate of several kilometers per second. The newly ionized gas is heated to tens of thousands of degrees, and it expands rapidly away from the globule, creating a flow of material that streams off into the surrounding nebula. This is the evaporation that gives the EGGs their name, a slow but steady loss of mass that will eventually consume the entire globule. But the evaporation is not uniform. The densest parts of the globule resist the radiation more effectively, while the thinner regions are stripped away more quickly. This differential erosion creates the characteristic shapes of the EGGs: elongated fingers, twisted columns, and delicate pillars that point toward the source of the radiation. We drift closer to the globule, examining its surface in detail. The texture is rough and irregular, with small protrusions and indentations that catch the light at different angles. Some of these features are the remnants of previous structures that have been partially eroded, while others are new formations created by instabilities in the evaporation process. Deep within the globule, hidden from our view, a protostar may be forming. The dense core of the EGG provides a sheltered environment where collapse can proceed despite the harsh radiation outside. If the protostar can grow massive enough before the globule evaporates, it will survive to become a new star. If not, it will be exposed to the radiation before it is ready, and its growth will be stunted or halted entirely. This is the drama of the EGGs, a race between creation and destruction, between the patient work of gravity and the relentless erosion of radiation. The outcome is uncertain, and it depends on factors that we cannot easily measure. The initial mass of the globule, the intensity of the radiation, the rate of collapse at the core. We watch as a small fragment breaks away from the main globule, torn loose by the force of the evaporation. The fragment tumbles away into the ionized gas, glowing briefly as it is heated and dispersed. This is the fate that awaits the entire globule if the collapse cannot proceed fast enough. A slow dissolution into the surrounding medium, a return to the raw materials of the nebula. But not all EGGs meet this fate. Some are dense enough and massive enough to form stars, despite the evaporation. We can see evidence of this in the jets that emerge from some of the globules, the telltale signs of active star formation within. These jets punch through the surface of the EGG and extend into the surrounding nebula, carrying away material and momentum just as they do in the Bok globules. One nearby EGG shows just such a jet, a narrow beam of glowing gas that emerges from the tip of the globule and extends for several light years into the surrounding space. The presence of this jet tells us that a protostar has formed within the globule and is actively accreting material. The star will survive the evaporation of its birth cloud, emerging into the open nebula as a young stellar object. We follow the jet to its terminus, where it creates a small Herbig-Haro object in the ionized gas. The bow shock is compact and bright, a miniature version of the larger structures we saw earlier. The jet is weaker than those from more massive protostars, but it is still powerful enough to shape the surrounding medium and announce the presence of the forming star. The EGGs are found in a specific region of the nebula, along the boundary between the ionized gas and the cold molecular cloud. This boundary is called the photodissociation region, and it is one of the most complex and interesting environments in the stellar nursery. Here, the chemistry of the interstellar medium is transformed by the stellar radiation, creating a rich soup of molecules and ions that glow with their own characteristic light. We drift along this boundary, watching as the radiation sculpts the edge of the molecular cloud into fantastic shapes. Pillars and columns rise from the surface, each one crowned by a dense EGG that resists the erosion. The pillars cast long shadows into the ionized gas, creating dark streaks that extend away from the source of the radiation. These pillars are sometimes called elephant trunks because of their elongated, curved shapes. They are among the most iconic structures in stellar nurseries, photographed by telescopes and featured in countless images of cosmic beauty. But they are also transient structures, lasting only a few 100,000 years before the radiation erodes them away entirely. The EGGs at the tips of the pillars are the last refugees of star formation in this region. As the pillars shrink, the EGGs are exposed to more and more radiation, accelerating their evaporation. Some will form stars in time, others will not. The process is stochastic, governed by chance as much as by physics. We pause at the tip of one of the pillars, looking out over the vast expanse of the ionized nebula. The view is breathtaking. A sea of glowing gas stretching to the horizon, punctuated by the dark shapes of other pillars and globules. The light is warm and golden, filtered through the dust that permeates the region. This is the edge of creation, the boundary between the cold darkness where stars are born and the warm light where they live out their lives. The AGEs are the last outposts of the molecular cloud, the final strongholds of star formation before the radiation claims everything. Their fate is uncertain, but their beauty is undeniable. We carry this image with us as we continue our journey, a reminder of the delicate balance between creation and destruction that governs the life of the cosmos. Chapter 17. The Stellar Winds. The young stars that emerge from the nebula do not simply sit quietly and shine. They are active, dynamic objects that interact powerfully with their surroundings. One of the most important ways they do this is through their stellar winds, continuous flows of charged particles that stream outward from the stellar surface and shape the surrounding medium. We approach a young star that has recently emerged from its birth cloud, a bright blue object perhaps 10 times the mass of our Sun. The star is hot and luminous, its surface temperature exceeding 30,000 degrees. At these temperatures, the outer layers of the star are so energetic that they cannot be held in place by gravity. Instead, they flow outward into space, creating a stellar wind that moves at thousands of kilometers per second. The wind is invisible to our eyes. It consists of individual atoms and ions, far too sparse to scatter light or create a visible glow. But we can see its effects on the surrounding nebula. The wind pushes against the interstellar gas, compressing it and sweeping it away from the star. This creates a bubble of hot, low-density gas around the star, a cavity carved out of the denser material of the nebula. We drift into this bubble, crossing the boundary where the stellar wind meets the interstellar medium. This boundary is called the termination shock, and it marks the place where the supersonic wind abruptly slows down and heats up. The shock is invisible, but we can sense its presence in the change of the surrounding environment, from the cold, dense gas of the nebula to the hot, tenuous plasma of the wind bubble. Inside the bubble, the conditions are extreme. The temperature exceeds 1,000,000 degrees, hot enough to emit X-rays that would be lethal to any unprotected life. But the density is so low that there is almost no material to carry this heat. The bubble is a paradox, incredibly hot but essentially empty, a void of blazing plasma in the heart of the cold nebula. The stellar wind carries more than just heat and momentum. It also carries magnetic fields, tangled loops of force that are anchored in the stellar surface and stretched outward by the flowing plasma. These magnetic fields fill the bubble, creating a complex web of invisible structure that influences the motion of charged particles. We watch as a stream of energetic particles spirals along one of these magnetic field lines, accelerated to tremendous speeds by the forces at work in the bubble. These particles are cosmic rays, the high-energy radiation that permeates the galaxy and occasionally strikes the Earth. Some of them originated in supernova explosions, but others were accelerated right here in the termination shock of a stellar wind. The bubble is not static, but growing, expanding outward as the stellar wind continues to blow. The rate of expansion depends on the power of the wind and the density of the surrounding medium. In some cases, the bubble can grow to enormous sizes, spanning tens of light years and encompassing entire regions of the nebula. But the expansion cannot continue forever. Eventually, the bubble will encounter obstacles, dense clumps of gas, other stellar wind bubbles, or the edge of the nebula itself. When this happens, the expansion slows or stops, and the bubble reaches a kind of equilibrium with its surroundings. We can see evidence of such interactions in the shape of the bubble. It is not perfectly spherical, but elongated and irregular, with bulges and indentations that reflect the structure of the surrounding medium. In some directions, the bubble has expanded freely into low-density regions. In others, it has been confined by dense material that resists the pressure of the wind. The interface between the bubble and the surrounding nebula is a region of intense activity. Here, the hot plasma of the wind mixes with the cold gas of the interstellar medium, creating intermediate temperatures and densities. The mixing is turbulent and chaotic, with eddies and vortices that swirl through the gas like cream stirred into coffee. This mixing region is where some of the most interesting chemistry of the nebula takes place. The high temperatures break apart molecules, while the subsequent cooling allows new molecules to form. The result is a rich soup of chemical species, including some that are not found anywhere else in the universe. We drift through this mixing region, surrounded by the glow of excited atoms and molecules. The light here is different from the light of the ionized nebula, softer, more varied, with subtle gradations of color that reflect the complex chemistry at work. This is the light of transformation, of old materials being broken down and new materials being built up. The stellar wind also carries away mass from the star, slowly but steadily reducing its total material over time. For a star like the one we are observing, the mass loss rate is perhaps a billionth of the star's total mass per year, negligible on human timescales, but significant over the millions of years of the star's life. This mass loss has important consequences for the star's evolution. As the star loses mass, its internal structure changes, affecting its temperature, luminosity, and lifespan. The most massive stars lose so much mass through their winds that they can shed half or more of their original material before they die. This material is returned to the interstellar medium, enriched with heavy elements that were forged in the star's core. We watch as a particularly dense stream of wind material flows away from the star, a gust in the otherwise steady breeze. This gust was probably triggered by an event on the stellar surface, a flare, perhaps, or an eruption of magnetic activity. The gust will travel outward through the bubble, eventually reaching the termination shock and adding its energy to the surrounding medium. The stellar wind is one of the ways that stars give back to the cosmos. Throughout their lives, stars take in material from their surroundings, the gas and dust of the nebula, the debris of previous generations of stars. But they also return material through their winds and eventually through their deaths. This cycle of exchange connects the stars to the broader ecosystem of the galaxy, making each star a participant in a cosmic economy of matter and energy. We take one last look at the stellar wind bubble before continuing our journey. The blue star blazes at the center, its wind streaming outward in all directions. The bubble glows faintly with X-ray light, a shell of hot plasma carved out of the cold nebula. It is a testament to the power of stars, their ability to shape their surroundings and influence the evolution of the cosmos. The journey continues, and new wonders await. Chapter 18. The Reflection Nebulae. Not all nebulae glow with their own light. Some shine only by reflecting the light of nearby stars, creating a softer, more subtle beauty that is no less captivating than the brilliant emission nebulae we have explored. These are the reflection nebulae, and they offer a different perspective on the interplay between stars and the interstellar medium. We approach one of these reflection nebulae, a cloud of dust that surrounds a young blue star. The nebula glows with a soft blue light, the same color as the star itself, but diffused and scattered by the countless dust grains that fill the cloud. The effect is ethereal, like moonlight filtering through a thin mist. The blue color is not a coincidence. It arises from the same physics that makes Earth's sky blue, the preferential scattering of short wavelength light by small particles. The dust grains in the nebula are typically smaller than the wavelength of visible light, and they scatter blue light more efficiently than red. This gives the reflection nebula its characteristic color, a cool blue glow that contrasts with the warm reds and pinks of the emission nebulae. We drift into the nebula, surrounded by the soft blue light. The illumination is gentle and even, without the harsh contrasts of direct starlight. The dust grains that create this light are invisible individually, but collectively they fill the space around us with a luminous haze. The dust in a reflection nebula is the same material that we have encountered throughout the stellar nursery, tiny grains of silicates, carbon, and ice, the debris of previous generations of stars. But here, the dust is not being heated or ionized by stellar radiation. It is simply reflecting the light that falls upon it, acting as a cosmic mirror that redirects the starlight in all directions. This reflection is not perfect. Some of the light is absorbed by the dust grains, warming them slightly and causing them to emit infrared radiation. Other light passes through the nebula entirely, continuing on its journey through space. But enough light is scattered to make the nebula visible, a glowing cloud that traces the distribution of dust around the central star. The structure of the reflection nebula is complex and beautiful. We can see streamers and filaments of dust, regions of higher and lower density that create patterns of light and shadow. Some of these structures are shaped by the radiation pressure of the star, which pushes on the dust grains and creates cavities and channels in the cloud. Near the star, the dust is being slowly destroyed by the intense radiation. The smallest grains are vaporized entirely, while larger grains are eroded and broken apart. This creates a dust-free zone around the star, a cavity of clear space where the reflection nebula cannot exist. The inner edge of the nebula marks the boundary of this zone, a sharp transition from darkness to light. Further from the star, the dust is denser and the reflection nebula is brighter. Here, the starlight has not yet had time to erode the dust, and the grains scatter light efficiently. The brightness of the nebula falls off gradually with distance from the star, following the inverse square law that governs all radiation. We pause at a particularly beautiful region of the nebula, where the dust has formed a series of parallel ridges that catch the starlight at different angles. The ridges glow with varying intensities, creating a striped pattern that resembles the ribs of some cosmic creature. This structure was probably created by a shock wave that passed through the cloud in the distant past, compressing the dust into these regular formations. The reflection nebula is not entirely blue. In some regions, the dust is dense enough to block the starlight entirely, creating dark patches that contrast with the surrounding glow. These dark regions are similar to the Bok globules we explored earlier, dense cores of material that may be collapsing to form new stars. We can also see regions where the color shifts from blue to red. This happens when the light has to travel through a long path of dust before reaching us, allowing more of the blue light to be scattered away and leaving only the longer red wavelengths. This reddening is the same effect that makes sunsets red on Earth, and it gives parts of the reflection nebula a warm, golden hue. The star at the center of the nebula is young and hot, probably only a few million years old. It has recently emerged from its birth cloud, and the reflection nebula is the remnant of that cloud, the material that was not incorporated into the star or its planetary system. In time, the stellar wind and radiation will disperse this material entirely, and the reflection nebula will fade away. But for now, the nebula remains, a beautiful testament to the connection between stars and the medium from which they form. The light that illuminates the nebula was generated in the star's core through the nuclear fusion of hydrogen into helium. That light traveled outward through the star's interior, was emitted from its surface, and then scattered by the dust grains of the nebula. The journey from creation to observation spans millions of kilometers and millions of years, a chain of cause and effect that connects the heart of a star to our wondering eyes. We drift through the reflection nebula, bathed in its soft blue light. The experience is peaceful and contemplative, a gentle contrast to the more dramatic phenomena we have witnessed. The reflection nebula does not shout its presence, but whispers it, a subtle beauty that rewards patient observation. As we leave the reflection nebula behind, we carry with us a sense of the quiet beauty that pervades the cosmos. Not everything in the universe is dramatic and explosive. Some of the most beautiful sights are the gentlest, the soft glows and subtle colors that require careful attention to appreciate. The journey continues, and new wonders await. Chapter 19. The Binary Star Nurseries. Most stars are not born alone. Throughout the stellar nursery, we find stars forming in pairs, triplets, and even larger groups. These multiple star systems are created when a collapsing cloud fragments into several pieces, each piece forming its own star. The resulting stars are gravitationally bound to each other, orbiting around their common center of mass in an eternal dance. We approach a binary protostar system, two young stars still embedded in their birth cloud. The stars are separated by a few hundred astronomical units, close enough to influence each other's evolution, but far enough apart to have their own individual disks of gas and dust. The two protostars are not identical. One is larger and brighter, having accumulated more material from the surrounding cloud. The other is smaller and dimmer, a stellar runt that may never grow as large as its sibling. This inequality is common in binary systems and arises from the chaotic nature of the collapse process. We watch as material flows between the two stars, drawn by their gravitational influence. A stream of gas connects the two disks, a bridge of material that allows the stars to share their resources. The larger star tends to capture more of this shared material, growing at the expense of its smaller companion. This is a cosmic example of the rich getting richer, a gravitational feedback that amplifies initial differences. The orbital motion of the two stars creates complex patterns in the surrounding gas. The disks are not circular but elliptical, stretched and distorted by the gravitational pull of the companion star. Spiral arms wind through the disks, created by the periodic gravitational perturbations as the stars orbit each other. We drift between the two protostars, surrounded by the swirling gas of their shared environment. The light here is complex, a mixture of the infrared glow from both stars and the scattered light from the surrounding dust. The two stars cast overlapping shadows, creating a constantly shifting pattern of light and dark as they orbit. The binary system is also producing jets, but these jets are more complex than those from single protostars. Each star has its own jet, and the two jets interact with each other as they expand into the surrounding medium. Sometimes the jets collide, creating shock waves and knots of glowing gas. Other times, they miss each other, creating parallel tracks that extend in opposite directions. The orbital period of the binary system is perhaps a few hundred years, long by human standards, but short by cosmic ones. Over the lifetime of the protostars, they will complete thousands of orbits, each one slightly different from the last, as the system evolves and the stars grow. We watch as the two stars approach their closest point, their periastron. At this moment, the gravitational interaction is strongest, and the effects on the surrounding gas are most pronounced. Streams of material are pulled from the disks, spiraling inward toward the stars. The jets flicker and brighten, responding to the increased accretion rate. Then the stars swing apart, heading toward their farthest separation, their apastron. The interaction weakens, and the system relaxes into a more quiescent state. The disks settle back toward their equilibrium shapes, and the jets dim slightly as the accretion rate decreases. This orbital dance will continue for millions of years, shaping the evolution of both stars and their surrounding environment. The gravitational interaction affects not just the gas, but also any planets that might form in the system. Planetary orbits in binary systems can be stable, but only in certain configurations. Planets that orbit too close to either star or in the region between the stars will be ejected from the system by gravitational perturbations. We drift outward from the binary protostar system, looking back at the two glowing points of light embedded in their shared cloud. The system is a reminder that star formation is not a solitary process, but a social one. Stars are born in groups, and they influence each other's development in profound ways. The stellar nursery is full of such multiple systems. We can see them scattered throughout the nebula, pairs and triplets and larger groups, all in various stages of formation. Some are widely separated, their components barely interacting. Others are so close that their disks have merged into a single circumbinary structure, a shared reservoir of material that feeds both stars. The most extreme multiple systems contain dozens of stars, all formed from the same parent cloud. These are the precursors of open clusters, the loose associations of stars that drift together through the galaxy for millions of years before gradually dispersing. The stars in such a cluster are siblings, born from the same material at the same time, sharing a common origin even as they pursue separate destinies. We pause to contemplate the social nature of star formation. The universe might seem like a lonely place, with vast distances separating the stars. But at their birth, stars are crowded together, jostling for position in the dense environment of the stellar nursery. The interactions that occur during this crowded infancy shape the properties of the stars for the rest of their lives. Binary stars are particularly important for our understanding of stellar physics. By observing the orbits of binary systems, astronomers can measure the masses of stars directly, something that is very difficult to do for single stars. These mass measurements are the foundation of our understanding of how stars work, how they evolve, and how they eventually die. We carry this knowledge with us as we continue our journey through the stellar nursery. The binary protostars fade behind us, their light merging into the general glow of the nebula. But their lesson remains, that stars are born in community, shaped by their interactions with their siblings and connected to each other by the invisible bonds of gravity. The journey continues, and new wonders await. Chapter 20. The Outflow Cavities. As we travel through the stellar nursery, we encounter vast cavities carved into the molecular cloud by the outflows from young stars. These outflow cavities are among the largest structures created by the star formation process, extending for light years through the dense material of the nebula. We approach one of these cavities, a great hollow space that opens before us like the interior of a cosmic cathedral. The walls of the cavity are lined with glowing gas, illuminated by the young star at the cavity's base. The light is reflected and scattered by the dust in the walls, creating a soft, diffuse glow that fills the entire space. The cavity was created by the jets and winds from the young star over thousands of years. The high-speed outflows punched through the surrounding cloud, pushing the gas aside and creating a channel of lower density. As the outflows continued, the channel widened and lengthened, eventually forming the vast cavity we see today. The shape of the cavity is not random, but reflects the physics of the outflow process. The jets from young stars are typically bipolar, emerging from opposite poles of the protostar. This creates two cavities, one on each side of the star, extending in opposite directions through the cloud. We drift into the cavity, surrounded by its glowing walls. The space is not empty, but filled with a thin, hot gas, the material that was swept up by the outflows and heated by the shock waves. This gas glows with its own light, adding to the illumination from the central star. The walls of the cavity are textured and irregular, with ridges and valleys that trace the history of the outflow. We can see layers in the walls, like the strata in a geological formation, each layer representing a different episode of outflow activity. The oldest layers are at the outer edges of the cavity, while the youngest are closest to the star. Near the base of the cavity, where the young star resides, the walls narrow to a point. This is where the jets emerge, still active and still carving new material from the cloud. The jets are visible as bright streaks of light, narrow beams that extend from the star and gradually widen as they travel outward. We follow one of the jets up through the cavity, watching as it interacts with the walls. Where the jet strikes the wall at a glancing angle, it creates a bright region of shock-heated gas. Where it travels parallel to the wall, it leaves the material undisturbed. The pattern of bright and dark regions along the walls tells the story of the jet's wandering path, its direction changing slightly over time as the protostar wobbles on its axis. The cavity is not sealed at the top, but opens into the surrounding nebula. The jets have punched entirely through the molecular cloud, creating a channel that connects the hidden interior to the open space outside. Light from external stars filters down through this channel, adding to the illumination of the cavity. We emerge from the top of the cavity into the broader nebula, looking back at the structure we have just traversed. From this vantage point, the cavity appears as a dark indentation in the glowing cloud, a shadow cast by the absence of material. The jets are visible as faint streaks extending beyond the cloud, Herbig-Haro objects that mark the furthest reach of the outflow. The outflow cavity is a temporary structure. As the young star matures and its outflows weaken, the cavity will gradually fill in with material from the surrounding cloud. The walls will collapse inward, and the space will return to its original density. In a few million years, there will be no trace of the cavity, only the star that created it, now fully formed and shining steadily in the darkness. But for now, the cavity remains, a monument to the violence of stellar birth. The peaceful appearance of the stellar nursery belies the powerful forces at work within it. The creation of new stars is not a gentle process, but a dramatic one, involving jets and shocks and outflows that reshape the surrounding medium. We drift away from the outflow cavity, carrying with us a sense of the dynamic nature of star formation. The nebula is not a static backdrop, but an active participant in the birth of stars, shaped and reshaped by the objects it creates. Chapter 21. The Triggered Star Formation. As we continue our journey through the stellar nursery, we discover that the birth of one star can trigger the birth of others. This process, called triggered star formation, creates chains of stellar birth that propagate through the nebula like ripples on a pond. We approach a region where this triggering is actively occurring. A massive young star has formed at the center of a dense clump of gas, and its radiation is now compressing the surrounding material. The compression creates new, dense cores, which in turn collapse to form new stars. The process is self-propagating, each generation of stars triggering the formation of the next. The massive star at the center of this region is a blue giant, perhaps 30 times the mass of our Sun. Its radiation is intense, ionizing the gas around it and creating a glowing bubble of hot plasma. The edge of this bubble is where the triggering occurs, where the radiation pressure compresses the neutral gas into dense, star-forming cores. We can see these cores along the edge of the bubble, dark silhouettes against the bright background of ionized gas. Each core is a potential star, waiting for the compression to push it over the threshold of gravitational collapse. Some of the cores have already begun to collapse, showing the telltale signs of protostellar activity, infrared emission, jets, and outflows. The triggering process creates a characteristic pattern of star formation. The oldest stars are at the center, near the original massive star that started the chain. The youngest stars are at the edges, in the cores that are just now being compressed. This age gradient is a signature of triggered star formation, a record of the propagation of the triggering wave through the cloud. We drift along the edge of the bubble, watching as the radiation sculpts the gas into new star-forming structures. The process is slow by human standards. It takes thousands of years for a core to collapse and form a star, but fast by cosmic standards. The triggering wave can propagate through a molecular cloud in just a few million years, creating hundreds or thousands of new stars in its wake. The triggered stars are not random, but organized. They form in clusters and associations, groups of stars that share a common origin and move together through space. These stellar associations are the building blocks of the galaxy's stellar population, the factories that produce most of the stars we see in the night sky. We pause to contemplate the cascade of creation that unfolds before us. One star forms, and its radiation triggers the formation of others. Those stars, in turn, trigger still more, and the process continues until the available material is exhausted or dispersed. The result is a burst of star formation, a cosmic baby boom that populates the galaxy with new stellar citizens. The triggering process also affects the types of stars that form. The compression by radiation tends to create smaller, denser cores than would form naturally, leading to a population of lower mass stars. This is why triggered star formation often produces clusters dominated by small red stars rather than massive blue giants. But the triggering is not always constructive. Sometimes the radiation is too intense, and it disperses the cores before they can collapse. Other times, the compression is too weak, and the cores remain stable without forming stars. The outcome depends on a delicate balance of forces: radiation pressure, gravity, thermal pressure, and magnetic fields that varies from place to place within the nebula. We watch as one of the compressed cores begins its final collapse, the moment when gravity overwhelms all other forces and the material falls inward toward the center. The collapse is rapid, taking only a few thousand years to convert the diffuse core into a dense protostar. A new star is being born, triggered into existence by the radiation of its massive neighbor. This is the cycle of star formation in the galaxy, a self-sustaining process where each generation of stars creates the conditions for the next. The massive stars that trigger new formation will eventually die, exploding as supernovae and dispersing their material back into the interstellar medium. That material will form new molecular clouds, which will produce new massive stars, which will trigger new waves of star formation. The cycle has been repeating for billions of years, ever since the first stars formed in the young universe. It will continue for billions of years more, until the raw materials of star formation are finally exhausted. We are witnessing one small part of this grand cycle, one link in a chain that stretches back to the beginning of time and forward to the distant future. We carry this perspective with us as we continue our journey. The stellar nursery is not just a place where stars are born, but a node in a vast network of creation that spans the entire galaxy. Each star we see is connected to countless others, linked by the processes of triggering and feedback that govern the birth of stellar generations. Chapter 22: The Gentle Return to Darkness. Our journey through the stellar nursery is drawing to a close. We have witnessed the birth of stars, from the first stirrings of collapse in the cold molecular clouds to the emergence of young stellar objects into the light of the nebula. We have explored the structures and phenomena that accompany this process: the jets and outflows, the disks and globules, the bubbles and cavities that shape the interstellar medium. Now we drift toward the edge of the nebula, where the glowing gas fades into the darkness of interstellar space. The transition is gradual, the light dimming slowly as we move away from the regions of active star formation. The colors shift from the bright pinks and blues of the ionized gas to the softer hues of the reflection nebulae, and finally to the deep black of the void. We pause at this boundary, looking back at the stellar nursery we have explored. From here, the nebula appears as a great cloud of light against the background of stars, a glowing island in the sea of darkness. We can see the structures we visited, the pillars and globules, the cavities and jets, as subtle variations in the overall glow. The nebula is beautiful, but it is also temporary. In a few million years, the star formation will cease, the gas will disperse, and the nebula will fade away. The stars it has created will drift apart, each one pursuing its own path through the galaxy. The nebula will become a memory, preserved only in the properties of the stars it has birthed. But even as this nebula fades, others are forming elsewhere in the galaxy. The processes we have witnessed are universal, occurring in stellar nurseries throughout the Milky Way and in galaxies across the universe. Star formation is one of the fundamental activities of the cosmos, a process that has been shaping the universe since the first galaxies formed billions of years ago. We turn away from the nebula and face the darkness ahead. The interstellar medium stretches before us, a vast expanse of thin gas and dust that fills the spaces between the stars. This medium is not empty, but alive with activity. Shock waves and magnetic fields, cosmic rays and radiation, all the forces that shape the evolution of the galaxy. Somewhere out there, in the darkness, new molecular clouds are forming. Gas is accumulating, drawn together by gravity and compressed by the passage of spiral density waves. In time, these clouds will become dense enough to collapse, and new stellar nurseries will be born. The cycle will continue, generation after generation, for as long as the galaxy endures. We drift into the darkness, leaving the stellar nursery behind. The light fades around us, and the stars become points of brilliance against the black velvet of space. The silence is profound, a peace that comes from the vastness of the cosmos and the slowness of its processes. This is the universe as it truly is, not a static backdrop, but a dynamic, evolving system where matter and energy flow in endless cycles. Stars are born, live out their lives, and die, returning their material to the interstellar medium. That material forms new stars, which live and die in turn. The cycle has no beginning and no end, only the eternal present of cosmic evolution. We float in this darkness, at peace with the immensity of space and time. The journey has shown us wonders beyond imagination, but it has also shown us the underlying simplicity of the cosmos. The same forces, gravity, radiation, magnetic fields, operate everywhere, creating the same structures and phenomena across billions of light years. The universe is vast, but it is also comprehensible, its secrets yielding to patient observation and careful thought. The stars shine around us, each one a sun with its own story, its own history of birth and evolution. Some are young, still glowing with the heat of their formation. Others are old, their nuclear fuel nearly exhausted, their end approaching. All of them are part of the same cosmic family, children of the stellar nurseries that have been creating stars since the dawn of time. We let ourselves drift, carried by the gentle currents of the interstellar medium. There is no need to hurry, no destination that demands our attention. The universe unfolds around us in its own time, revealing its wonders to those who have the patience to observe. The darkness is not empty, but full of potential. Every atom of gas, every grain of dust, carries within it the possibility of becoming part of a star, a planet, perhaps even a living being. The raw materials of creation surround us, waiting for the right conditions to begin their transformation. And somewhere in the depths of space, those conditions are being met. A cloud is collapsing, a core is forming, a new star is being born. The cycle continues, as it has for billions of years, as it will for billions more. We close our eyes and let the peace of the cosmos wash over us. The journey is complete, but the universe goes on, creating and destroying, building and dispersing in the endless dance of cosmic evolution. Sleep now and dream of stars being born in distant nebulae. Dream of the gentle gravity that draws matter together, the patient processes that build worlds and suns. Dream of the light that will shine from those new stars, illuminating the darkness for generations yet to come. The universe is at work, even as you rest. And when you wake, the stars will still be there, shining with the light of creation, reminding you of the wonders that await in the depths of space. Rest now. The cosmos holds you in its gentle embrace, a child of the stars returning to the peace from which all things emerge. Closing meditation, the lullaby of light. As we conclude our journey through the stellar nurseries, let us carry with us the peace we have found in these cosmic spaces. The universe, for all its vastness and complexity, operates according to principles of profound simplicity. Gravity draws matter together. Heat and pressure resist the collapse. Light carries energy across the void. These simple rules, playing out over billions of years, create all the wonders we have witnessed. The stars that form in the nebulae will shine for millions or billions of years, warming any planets that orbit them, providing the energy that might one day power the processes of life. The heavy elements forged in stellar cores will be scattered into space when those stars die, enriching the interstellar medium with the raw materials for future generations of stars and planets. We are part of this cycle. The atoms in our bodies were forged in ancient stars, scattered by supernovae, gathered into the molecular cloud that formed our solar system. We are, quite literally, made of star stuff, children of the stellar nurseries, inheritors of the cosmic legacy of creation. This knowledge can bring us peace. We are not separate from the universe, but part of it, woven into the fabric of cosmic evolution. The same forces that shape the nebulae shape us. The same processes that create stars create the conditions for life. We belong here, in this vast and ancient cosmos, as surely as the stars belong in the sky. So rest now, knowing that you are held by the same gravity that holds the stars in their courses. Let the gentle light of distant nebulae fill your dreams, and know that somewhere in the depths of space, new stars are being born, new worlds are taking shape, and the universe continues its endless work of creation. The stellar nurseries will still be there when you wake, glowing with the light of young stars, filled with the promise of worlds yet to come. The universe is patient, and it will wait for you to return to your contemplation of its wonders. Until then, sleep well, cradled in the arms of the cosmos, dreaming of nebulae and star nurseries and the gentle gravity that binds all things together. Good night. End of script. Total approximate word count, 2,350 words.